he could go out periodically and scrape off barnacles of the removed species if they had attached. That barnacles have a larval phase where they move around and then they settle and stay where they are. That way, in that way, they're like plants. Once they're post-larval stage, they're not going anywhere. So he could remove them. So after whatever amount of time his experiment took, he went back out. And here's what he noticed, is that when these barnacles had been removed, new individuals of this species were here. They had settled here. The larvae had. When these barnacles were removed, the members of this species stayed where they were. They did not settle in the new area that was open to them. So he could say, hey, this is really cool. This is evidence, experimental evidence out in the field of all things, so that's really cool, of interspecific competition leading to niche partitioning, which increased the biodiversity of the community, made the community more biodiverse. So that structure, when we're talking about community structure, we're talking about what's there. And we're talking now, instead of just one species of barnacle being here because this one was driven to extinction, these guys accept a less than optimal habitat. That also allows us to investigate two other ways of dividing up niche, and that's by fundamental and realized. The fundamental niche is the entire niche that the individuals of that species could use, whether it's time, space, or resources. And for this species, the fundamental niche is from here to here. Okay? Its realized niche, where it is found, and this is a place niche, is only from here to here. Interestingly, so notice that the realized niche is not as big or as extensive as the fundamental niche. With this species, and again he showed this, he had evidence for this, that the realized niche and the fundamental niche are the same. That this species will be found here even if it has the ability to expand. Alright, so I thought that was pretty neat. Just a little bit about how predator-prey interactions influence the structure of communities. And it's a biotic factor, like interspecific competition. And in some cases, predators play a really big role. For example, out in the Salish Sea, the sea otters. The sea otters eat sea urchins. Hey, we've talked about sea urchins now. This is the third time. The sea otters eat sea urchins. If the sea otters are taken out, if that predator is taken out, the sea urchin population increases dramatically, and the sea urchins then eat up all the kelp, and then the populations of the other species crash. So this once incredibly diverse community is no longer diverse. The structure has changed dramatically, and that is because one species, a keystone predator, was taken out. We know that wolves are keystone predators. We know that sea stars are keystone predators in certain areas because of research people that have done. And in this case, this was another one with moose and wolves. But another pattern I want you to see which would be indicative of the role of the predator on the prey population and keeping everything in check, is looking at what's going on with carrying capacities. Now, these are different numbers. There are far more moose than there are wolves. But if we look, the moose population is oscillating around a carrying capacity. The wolf population is oscillating around a carrying capacity, and they are oscillating out of sync. Do you see that? So that when we look at the moose, there's increase, increase, increase. Oh, hitting that area where there's a lot of moose, but when there weren't as many moose, that led to fewer wolves. Not right away. It's a little behind because it oscillates out of sync because they don't have enough food. And then when the moose population has been increasing, then with a lag time, the wolf population increases. This is interesting because at the end, and that was, looks like toward the end of the 1990s, I can't really tell that easily. I can't read it as well as I'd like to. But the moose population was going up quite a bit, but notice the wolf population has been decreasing. This might be due to hunting or a disease in the wolf population. And this could cause a real problem. This is, again, a keystone predator. If the wolves were taken out or almost taken out, the moose population continues to grow, and then they overeat their resource. Plus, if they're a superior competitor, outcompete other species, especially herbivores, for that resource, that could have a dramatic change on that community and decrease the biodiversity, the number of the different species in the area. Now, I studied predator-prey, a predator-prey relationship for my dissertation, so I just can't leave this course without talking a little more about predators and prey. So obviously predation is good for the predator. It gets something to eat. It gets to feed its babies, either whether they're forming eggs or they're inside them or they're feeding them at a nest or whatever. And it's bad for the prey. So with adaptation, in fact, we talk about coevolution between predators and prey. The prey tend to acquire adaptations that help individuals keep from being eaten. Okay? And I have some here like crypsis, running away, fleeing, so being fast. Mechanical barriers, like the porcupine has the quills. Chemical deterrence, and mimicry. Okay, so let's look at a few of these. Crypsis. Crypsis is blending in. So here's a seahorse, and I believe this is it's not a sea star, it's another echinoderm. I'm not sure what echinoderm it is, but look how much this seahorse looks like it. So it would be hard for a predator to notice this potential prey item. The octopi are so cool, like how they can just, change color and blend in with their environments. You should look that up online. It is really neat. So just blending in and avoiding the predator in that way. Aposematic coloration, which are warning colors, go with being noxious or tasting bad or toxic, and actually being worse than just tasting bad, maybe debilitating the organism, in fact, to the point of death. And this is a coral snake of North America. So you see that, and you've heard that little thing, red touches black, friend of Jack, red touches yellow, see, kill a fellow. So, by the way, that doesn't work in South America. So if you go down there, just don't pick up any snakes, okay? Unless you really, really know a lot about snakes. Not think you know a lot, but really, really do. Coral snake patterns are completely different. And yeah, you don't want to be. Plus, if you put your hand in a hole, you might get bit by a fer-de-lance or a bushmaster, and then, well, you could die. So then, yeah, you want to be really careful with snakes in South America and other places as well. Okay, so aposematic or warning coloration. Then I had the mimics. So this is not a coral snake, remember? Red touches black, friend of Jack. Red touches yellow. It's not really yellow. It's more of a whitish color, but kill a fellow. But this red and black coloration is supposed to confuse predators so that predators might very well avoid this snake too because it sees this red color. And a lot of these warning colors are really bright and noticeable colors so that predators can readily see them and avoid the prey avoid predation. Then there are the Mullerian mimics, where they are all toxic or all noxious, but rather than having different patterns, it's the same pattern repeated. So orange and black in these butterflies, yellow and red in many wasp and other hymenopterids like bees are also yellow and red a lot of times. I mean yellow and black, sorry, yellow and black. So those are Mullerian mimics. Mullerian mimics, all of them pack a punch, where the Batesian mimics, they are harmless mimics. Posturing. If you see one of these and you're eating a sandwich, you probably shouldn't pick it up and then continue to eat your sandwich. This is a rough-skinned newt. Excuse me. And this rough-skinned newt is very, very toxic. And if it is alarmed by a potential predator, it will posture. So it has aposematic coloration, which usually you don't see, but if you poke at it, it'll flip its head back and flip its tail over a little bit so you can see that orange, so that a potential predator, which you would be seen as a potential predator, but you would never eat one, would leave it alone. So this is posturing together with aposematic coloration that is due to being highly toxic. So you see how there's overlap in these categories. So if you look at the end of your notes, there are characteristics that are common to all ecosystems. And what I want you to look at those, like they all have producers, they all have consumers, they all have nutrient cycling, etc. Another thing is that they are, over evolutionary time, there's almost like an adaptation at the community or ecosystem level, so that they work together. Like I had said, you wouldn't, or did I say this? But you wouldn't throw randomly a piece of car equipment into your engine because it could throw everything out of whack. Likewise, adding to or taking away something from an ecosystem, whether it's an abiotic factor or a biotic part, could have a negative effect. I end with this slide because I just wanted some pretty pictures. One of the things that makes me love biology so much is what is out there in the world. You know, a road with a canopy over it, and while you don't see a bunch of animals, they're there. While you don't see fungi, they're there. While you don't see the protist, they are there. This lovely photo with this sea turtle. I like reptiles a lot, so there's that sea turtle and some coral and just an amazing ecosystem there. The desert, but I have the close-up of the horned lizard. I've always loved horned lizards. I thought they were so cool. And then this interface with terrestrial and aquatic. So just amazing out there. And yeah, so I hope that you do really well on your final, and I hope that you stay healthy and that life settles down pretty soon for all of us. And best of luck with your future academics, endeavors and your careers. Okay, bye.